Hello there.
Hey, Zach, only you can hear me.
With the ground beneath your feet, with a whisper in the trees. Do you feel us watching? Hunger in our eyes, victories on our minds. It's our time to rise. Can you hear the sound? Can't stop us now. We're not backing down on what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. We're not backing down on what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. Say I'm good-hearted, but I'm just getting started. Got my eyes on the target. No, no. Till the battle's won, till kingdom come. I'll never run. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. They say I'm dangerous 'cause I broke all the cages. No, I won't sit and take it. No, no. They left me for dead, I guess I'll never learn. Every time I break, there's just more pain to burn. They'll never, never, never learn. Till the battle's won, till kingdom come. I'll never run. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. They'll be calling me royalty.
Good evening and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. We are doing some math tonight. Let's see. I think we possibly need to reduce that again. Which is slightly absurd because it's already like at about 4%. How's everybody doing tonight? Evening, Zach. Move these back where they were. It's probably better, honestly. That's good. All right, lock them in the corners. And with the math night, we can stick the webcam also in the corner. And put the Ko-Fi back over our head here. Cool. All right. So I hope everybody's having a good evening. Notice that we had a few additions to the mathematics section. Hey, how's it going? And a Happy New Year to you as well. I don't think I'm usually much help in the mathematics section. We can see if there's anything that I can remotely understand. Doesn't seem to be a lot. Ooh, that one actually. Stability of time periodic solutions to Navier-Stokes Fourier system. That seems somewhat understandable. They seem to have put almost the entire abstract in here, and it's line break. Yeah, the line break is weird. Or if anybody else wants to see one and discuss it, I may not need to understand it. Slightly disappointed in this coffee. Not only because it was about 4 times as expensive as any normal coffee, but it's just not good. Repair scheme for a distributed storage system based on multivariate polynomials. That seems interesting if, you know, again, completely indecipherable. That'd be fine. This one too. Largest common subtree of two random trees. I've done some amount of, not exactly work, but I've done some amount of studying of search trees and things like that, so this could be interesting. Permutation group of Reed-Solomon codes over arbitrary points given by polynomials of degree 1 that leave the set of evaluation points invariant. Yeah. That's close to something that I could understand. Type paths and fully directed hypergraphs. Grid designs. PDEs are another one that, like, I could probably understand it. Sure, we'll throw that out there too. We will attempt to look at these four today. Just popping back to some earlier ones that I had up. Right, linear geometry was something that Stuckey wanted to look at, despite me not. You know, I can sort of get what they're getting at, but there was a lot of discussion, which could be a good thing. Elementary proof of minimax we talked about. And, ooh, 2 of 2 entries. Oh, yep, okay. Here we go. I mean, we've got a lot since basically Christmas. Research projects and Moscow Mathematical Conference for high school students. That seems pretty good. It is in Russian language, so that's a small barrier for me. Just out of curiosity. Yeah, okay. Let's save the linear geometry one. New folder. We'll put papers to discuss on there. Amicable numbers and their connection to the Euler-Totient function. We talked a little bit about Euler's Totient function. We were doing something recently. Note on the Legendre transformation. Symplectic geometry. X plays Pokemon for almost every X. Curious. We'll poke into that maybe a little bit. Galilei and Huygens, Music and Science. On the Picard-Lindelöf argument and the Banach-Cacciapoli contraction mapping principle. I have no idea what this is, however, and whenever people's names are brought up in connection with a lot of this stuff, like, I have no idea, because I just have not been, I have not learned a lot of their, you know, common names and things like that, so we'll pop that up just in case, because it is ODEs, so in theory we should know some. The story of geometry told by coins. Canadian Numismatic Journal. Interesting. Interestingly enough, the 50p, the 50 pence piece in the UK is a, I think, heptagon. And it's been working really well to, like, curb some of the issues that they've had and make sure that it works efficiently in vending machines and, like, all this other stuff. So I don't know exactly what it might say, but still. Mathematics in the liturgical books of the Catholic Church. Phases of ecclesiastical moon. When mathematics meets painting, Fibonacci geometry, cubism, and visual abstraction. Yeah, sure. I'll pop that one up too. Alright. Got a lot to look at. Taffy Tree and Tangles was one that we pulled up a while ago. Oh. Study the relationship between three combinatorial objects, a taffy pulling machine, the Calkin Wilf tree of all fractions, and Conway's rational triangles, or rational tangles. After introducing these objects, we develop a Taffy analog for Conway's characterization of rational tangles and give a direct geometric connection between rational tangles and taffy pulls. Taffy pulling machine is a very interesting machine, and yeah, I can understand how it would do something with, you know, how there'd be some sort of math that goes with it. But essentially, you've got three pegs that are working on a, I want to say lemniscate shape, but it could just be that, like, I think most of the time they have four, and they kind of go around like this, you know, 1, 2, 3, 4, almost like gears. Hey Rex, how's it going? And they like the pegs essentially dive into the middle, grab the taffy candy, and then move to the outside, and it pulls it. And naturally, this ends up like being able to stretch this stuff until you get a very, well, until you have a pliable mixture of of the taffy. There was a short that I saw recently of a teenager who was taking the taffy, throwing it over the hook herself, and then, you know, leaning back until she got down to, I don't know, a few feet long, snapped it together, mixed a couple of things, and then tossed it back over the hook again to pull again. And I think she was saying the issue here was that the hook was too high, and somebody was like, "Oh, you should lower the hook for your short employees," or something like that. And the girl's like, "It's fine," and just keeps, you know, is able to keep doing it. And then, like, the dad comes over and is like, he's much taller, so he has a much easier time of doing it. You know, you just kind of sink. And then he was like, "All right, let me try from, like, your height," and, like, you know, bent himself over a bit and tried to go from there. And he said it was much harder from that position. Anyway. Multiple ways to represent the same mathematical concept often has advantages. Take, for instance, the problem of dissecting a square into smaller unequal squares, which gained notoriety in early 20th century. Initial searches did not yield any solutions, leading many to question whether such a dissection was possible. When then college students, Brooke, Smith, Stone, and Tute, became interested in the problem, they realized that square dissections correspond to certain electrical networks, allowing them to apply established theory from electrical engineering to discover new construction methods. Insight from this second representation of the problem led to a breakthrough in finding the first squared square consisting of 69 tiles. Each representation of a concept may offer its own advantages, such as notational ease or conceptual simplicity. If nothing else, the joy of connecting multiple representations will make the mathematician smile. Usually. We hope to foster that experience by connecting three combinatorial objects from literature: taffy pulling machines, the Calkin Wilf tree of all fractions, and Conway's rational tangles. Yeah, here we go. Taffy is a candy made from a heated sugar mixture. As it cools, the taffy is pulled, a kneading process that incorporates air to make the taffy soft and chewy. If you have never had saltwater taffy, definitely head to one of the seacoasts. It doesn't matter which one, but, you know, New Hampshire's better. And go find some saltwater taffy. It is not made from saltwater. It is just regular sugar. There's a reason. You can look it up. Taffy pulling can be done by hand or with a machine. There are numerous designs of taffy pulling machines that are used commercially and have various mathematical properties. See Tifo. Figure 1 below is a, well, no, there is no figure here, but a 3-peg taffy pulling machine has an arrangement like this. In this paper, we considered the design patented by Nitz in 1918. There we go. Alright. You jerks. Alright. You can look up the Nitz taffy machine as well. It has 3 large pegs that rotate around each other in figure 8 motions. A confectioner loads the machine by attaching a wad of taffy to the leftmost 2 pegs. When the machine runs, the motion of the pegs can be simplified into 2 actions. A right turn, in which the rightmost 2 pegs trade places by rotating clockwise, and a left turn, in which the leftmost 2 pegs trade places by rotating counterclockwise. In each case, the middle peg will rotate upward and outward. Okay, so yeah. In this case, we see that this is going to switch by coming over here. It pulls the taffy over. This peg comes under and then ends up tagging the middle of the taffy here. And then it will then move in the counterclockwise direction, continuing its motion from the center then to the outside by pulling the taffy up. That then allows it to have this whole wrapped motion. And then this one right here is going to be the next one that comes up and around, and then continue out and around that way. Or this one goes to here, this one comes to the center, and then it goes immediately into the other loop as well. We define a taffy pull to be any finite sequence of left and right turns in order. For example, we write t equals RRL or R squared L to denote the taffy pull made by 2 right turns followed by a left turn. We include the sequence of 0 turns and call it the initial taffy pull and denoted T0. Knit's machine is designed to make alternating left and right turns. Continuing from figure 2, figure 3 illustrates how the taffy folds as the machine makes 3 more turns. So we had the first one up top there. We have the second one in which, again, the middle peg has now moved in a full circle. Middle peg has now moved in a full circle to come around. In here, that peg is now going to make another left full turn to get back to the middle. Here. Is it? No. Okay, it's just made the half turn to get over to the left-hand side, which is what we see here. Right, and then this middle one now turns to the right, ends up at the rightmost spot here. Taffy diagrams are cross-sectional views of the taffy in the machine. To balance the representational accuracy with visual clarity, we abide by a few conventions. Strands of taffy that touch each other will stick together in practice, but for better visibility, we leave small gaps to nearby strands. Besides, adding more air makes the taffy better. So clearly, the mathematical representation is just going to be nice, airy taffy that doesn't technically exist. The aim of pulling taffy is to trap air bubbles between the many folds. The amount of air trapped is roughly proportional to the number of layers of taffy, where a layer represents a horizontal segment of taffy between adjacent pegs. An effective taffy machine produces increasingly many layers of taffy in each turn. Obviously, at some point, it's actually going to break apart and then come together with the other folds that are on top of it or underneath it, but you know, again, mathematical taffy. Spherical cow and all that. To measure effectiveness of the knits machine, we calculate the total number of layers of taffy n. Total number of layers of taffy after n turns and determine the growth rate of this quantity with respect to n. TIFO similarly defines the efficiency of the taffy machine in given paper. For the purpose of counting, it helps to distinguish layers of taffy appearing between the leftmost 2 pegs as left layers and those appearing between the rightmost 2 pegs as right layers. For a taffy pull T, we write T sub L to denote the number of left layers and T sub R to denote the number of right layers, as in the table. These numbers are obtained by the diagram of T by drawing vertical lines between adjacent pegs. Right. And as it turns out, counting the left and right layers of taffy pulls made by Knit's machine reveals a similar pattern. 1, 1, 2, 2. Oh dear. 5, 5. Ah, well. 0, 1, 1, 3, 3, 8. 8. Indeed, the layer counts are all Fibonacci numbers. After n turns, the number of left and right layers are f sub n plus 1 and f sub n respectively if n is even, or f sub n and f sub n plus 1 if n is odd. To see why this pattern continues, we demonstrate the general pattern You have a plan to make a single strand stretchy noodle. There was a video that we saw in Physics 1 back in 9th grade that had a guy making like the traditional noodles by hand. I don't remember. He was a Chinese chef. I don't remember where he was from. San Francisco, maybe? Yeah. It's been a really long time since I watched that video. Yeah, it's pretty close to 30 years. Oh. I gotta find that again. Okay. Let T be a taffy pull with TL left and TR right layers. When T is extended by a left turn, right layers of T get stretched to the left, and left layers of T rotate underneath, demonstrated by figure 5 here, where layers are shown in thickened middle section for clarity in the visualization. When turn is complete, the resulting taffy pull T prime equals TL. Has layer counts T prime sub L equals T sub L plus T sub R, and T prime sub R equals T sub R. Similarly, extended by a right turn does the other. We apply this result to the count. In the layers made by the knits machine, initial taffy pull has 1 equals F sub 1 left and 0 equals F sub 0 right. The machine makes a right turn, resulting in taffy pull. The resulting taffy pull still has F sub 1 left, but now has F sub 2, which equals F sub 1 plus F sub 0 right layers. Then a left turn is made, resulting is F sub 3, which equals F sub 2 plus F sub 1 left, and F sub 2 right layers. Alright, follows that after n alternating turns, the numbers on left and right layers are F sub n plus 1 and F sub n respectively, if n is even. Right, we just said that. Measure effectiveness of the knits machine. After n turns, the taffy pull has a total number of layers T sub L plus T sub R equals F sub n plus F sub n plus 1, which is F sub n plus 2, again Fibonacci. Hence the nth turn increases the total number of layers by a factor of F sub n plus 2 over F sub n plus 1, which we all know approaches the golden ratio of 1 plus root 5 all over root 2, approximately 1.618. As n grows. Accordingly, the total number of layers after n turns. It's too bad I'm not wearing my, or I don't have one, but it's too bad I don't have a Phi shirt, because that would have worked very well here. Accordingly, the total number of layers after n turns is asymptotic to Phi to the n divided by root 5. Exponential growth of layer counts is common among conventional taffy machine designs, but the growth factor varies between them. Is F sub n plus 2 total layers after n turns optimal for a 3-peg taffy machine? To answer this question, we consider other turning sequences combinatorially. Beyond Knits' machine alternates turns. The alternating turns produce taffy pulls with Fibonacci numbers of layers. What about other sequences? You can imagine a taffy machine that can make any sequence of left and right turns upon request, and so could produce any taffy pull. What is reasonable? Is it reasonable to ask which pairs of integers can be the left and right layer counts of some taffy pull? It is reasonable to ask which pairs of integers can be left and right layer counts of some taffy pull. Taffy pulls can be arranged in a binary tree, where each node has 2 children called left child and right child. Left and right children of a node labeled by taffy pull T are extensions of T by a single left or right turn respectively. Extending the initial taffy pull T sub 0 by left does not change the diagram, so we omit the left branch for the first step. Right, it's boring. It just flips it over. Taffy diagrams in Figure 6 are distinct, suggesting that each taffy pole beginning with a right turn has a distinct diagram. What if you add more nodes? Yes. So, I'd also said I have seen them that have 4 pegs, and they're arranged like this, so that they're always perpendicular to each other. And as one rotates, so does the other. So they'll go through each other like that. That one also works, but I think the issue is that at some point, if it does this, right, if it rotates like this, they're going to end up... No, it's okay. I was worried that at some point it was going to be pulling the taffy down, which would be a bad idea because then you risk dropping some. But here, it's the same as this other one. The one in the middle is always going up. So it's always pulling taffy like this. You know, it's always coming up through the middle. So that's okay. Denote the downward path in the tree to the taffy pole T equals Rn1, Ln2, etc. to Rnk using same notation Rn1, Ln2, ... Rnk. And each taffy pole T, we write the ordered pair T sub R, T sub L to denote the numbers of left and right layers of T. Seemingly reversed order is intended to make the following connection more intuitive. We determined in the previous section that the left child of a node labeled with taffy pole T has layer counts TR, TL plus TR. And right child in layer counts will have layer counts TL plus TR, TL. We hope that some readers may recognize this pair of generating actions as what has become known as the Calkin-Wilf tree, binary tree of fractions with root 1 over 1, in which the left child of A over B is A over A plus B, and the right child is A plus B over B. Call these generating actions left rule and right rule, respectively. To make the correspondence explicit, we assign each taffy pole T with layer counts TRTL, taffy number Q of T equals TR over TL, then T and Q of T are located at the same nodes in the taffy tree, in the tree of taffy poles and Calkin-Wilf tree respectively, as seen in Figure 7. Now, I have also seen this. This is what exists in the ratios between... Y'all are gonna absolutely hate this, I think. But nope, it isn't. Never mind. I was thinking this is the same thing that exists with the Pascal triangle, but it isn't. It's not quite the same. Right, the top really doesn't have one, but the multiplier between the values on the Pascal triangle between your 1 and 1 is 1. Between your 1 and 2, it has a ratio of either 2 to 1 or 1/2, depending on which way you're going. And then the other one, the reciprocal, when you go to the other number. So 1 to 2 to 1 is a ratio of 2 to 1, ratio of 1 to 2. Then 1, 3, 3, 1 is where it breaks here. So it's a ratio of 3. Let's stick with these numbers. So 1 to 3 but then it should be 3 to 3, which is 1, which is not what that represents. So it is not going to be represented in this particular case. What if the node's movements are stochastic? So I think they were referencing that at some point there, where, like, the binary tree is determining whether you have picked one or the other. So, right, if you assign certain probabilities to each one, that in a particular arrangement, a left or a right turn will have certain probabilities, then it will end up with you'll end up with a particular stochastic sequence. So I'm not really sure how to. I can make that work, I'm sure. We could go over to Python and spend all my time again. Positive integer n, we're interested in determining which sequence of n turns produces a taffy pull with the most layers, TL plus TR, since this number is roughly proportional to the amount of trapped air in the taffy. Largest total corresponds to the largest numerator-denominator sum among all fractions in row n of the Calkin-Wilf tree, which in turn is the largest numerator or denominator in row n plus 1. Largest numerator in row n is the Fibonacci number f sub n plus 1. Hence, the largest total number of layers in the taffy pull made by n turns is going to be f sub n plus 2, showing that the alternating turns performed by the Nitz machine is the most effective strategy. Chaos Taffy. While Taffy diagrams are visually appealing, a more useful representation for answering certain questions may be found with Taffy numbers. In the previous section, we found that all Taffy pulls beginning with right turn have distinct diagrams. Given one of these diagrams, we may wish to recover the sequence of left and right turns that generated it. I'm not breaking up on my Taffy to figure out what layers are where. We see from figure 6 that diagrams of Taffy pulls below t equals r are lopsided, having more mass to the left or to the right of the center peg depending on the final turn. With some effort, the diagram can be redrawn with the final turn undone. This process can be repeated to identify the penultimate turn and so on and so forth backwards, eventually obtaining the sequence of turns that has generated the diagram. Each iteration makes a single step up to up the tree of Taffy pulls, and doing so is rather laborious. Yes, it will. You might as well jam your entire machine with just string and do it that way. Alright. Changing representations allows us to work directly with Taffy numbers, which turns out to be far more convenient. Again, A over B is left if A is less than B, and right if A is greater than B. Parent of A over B is found by subtracting the smaller from the larger. Procedure for stepping up the tree one level at a time is essentially the same as the algorithm in Proposition 2 of Euclid Elements, Book 7, for finding greatest common divisor of A and B, sometimes called the slow Euclidean algorithm, which proceeds by subtraction rather than division. Nice. Writing Taffy pulls in terms of consecutive runs from the same type provides a connection to the better-known fast Euclidean algorithm, which replaces the larger of A and B with the remainder upon division by the smaller. The integer quotient counts as the maximal number of consecutive subtractions of one number from the other, so each iteration of the algorithm slides up the Calkin-Wilf tree along maximal run of steps in the same direction. Quotients obtained from successive iterations of the fast Euclidean algorithm are the coefficients of a continued fraction for a over b. Hence, the path from 0 over 1 to a over b in the Calkin-Wolf tree corresponds to the continued fraction of a over b, whose coefficients are the numbers of consecutive steps in each direction along the path. Explicitly, the path ends at the rational number with the continued fraction representation nk, nk minus 1, etc. to n sub 1. Figure 8 illustrates the path from 0 over 1 to 9 over 7, corresponding to the continued fraction for 9 over 7. So 1, 3, 2. It's going to be... Okay. Yep. Coming from... So for this... Oh, okay, yeah. So we're adding whichever one we feel like to the other in order, in this case, to find 9/7. Or coming from 9/7, we're able to then do subtraction to get back up the chart. Once we do that, we find that we have 1 right, 3 left, and 2 right, which would have gotten us to our current location, 9/7, which in doing so, 1, 3, 2. This gets us a 1 on the outside, plus 1 over 3, plus 1 over 2. So that continued fraction is going to be the proper representation, improper representation of 9/7, which is itself an improper fraction. Okay. Just talked about the fact that it's a reverse turn and all that good stuff. Reverse turn undoes corresponding forward turn, so therefore L inverse R inverse. Define reverse Taffy pole to be any finite sequence of reverse left and right turns. Naturally, we wish to assign a Taffy number to each reverse Taffy pole. Can be done following observation that left and right rules generating Calkin-Wolf tree are invertible. Parent of the left is A over B. Nope. Of left child A over B is A over B minus A. And parent of a right child A over B is A minus B over B. Call these operations backward left, backward right, respectively. Right? Each rational number appears exactly once in the double tree of fractions. Or in just the lower one, we get every positive rational. So having both the positive and the negative, we're going to get all possible rational numbers eventually. Hence, double tree of Taffy poles has a representative for each Taffy number. We call a Taffy pole in the double tree the canonical Taffy pole, or its Taffy number. These are forward and reverse Taffy poles beginning with R or R inverse, as well as T0. Boy. Diagrams of canonical Taffy poles, as seen in Figure 10, are related by rotational symmetry. If the diagrams of T and T prime are 180-degree rotations of each other, right, and also numerical negatives, that's all good. Additive inverses. QT and QT prime are negative reciprocals of each other. Yep. For instance, canonical taffy poles, T equals right, left, right, and T prime is equal to right inverse 2, left inverse 1. Have diagrams that are 180-degree rotations of each other. And their taffy numbers are Q of T is 3 over 2, and Q of T prime is negative 2/3. No taffy pole has a diagram that is the 180-degree rotation of the diagram of the initial taffy pole T0, right? It is its own inverse, essentially. Nope, never mind. It is not. In lieu, we use T infinity as a symbolic placeholder. Okay, fair. Ow, 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 ow. Yes, okay, right. In which the taffy connects the two rightmost pegs, because we don't do that. Never mind. I get it. Taffy number of T infinity is then Q of T infinity equals 1 over Q of T0, which is negative 1 over 0, which is 1 over 0, which is T infinity, or which is infinity. Infinitely long. We let T infinity be the canonical taffy pole for the taffy number 1 over 0, and now the 180-degree rotated diagram of each canonical taffy pole is the diagram of another canonical taffy pole. This is the infrastructure we need for the next section. Freely turning taffy machine can make a taffy pole with any rational number. What about a machine that can make both forward and reverse turns in any order? So we define the generalized taffy pole. Think, here you go, Rex. Here's what you... Another thing you may have been alluding to. For example, T equals R2L R inverse is a generalized taffy pole that is neither forward nor reverse. We wish to assign a taffy number to the generalized taffy pole. We already have a system in place. Starting with 0 over 1, apply left, right, backward, right, until you get the number. So we have here, right, this is 2 rights to get us to 2 over 1, a left to get us to 2 over 3, and a backward right, nope, yes, backward right to get us to negative 1/3. Since pairs of turns left, left inverse, right, right inverse, left inverse left, and right inverse right have no net effect on the taffy machine or taffy number, we adopt the convention that such pairs will be collapsed. So that, for example, right inverse right 2 left is written more simply as right left. And every taffy pole can be written in standard form. Again, rights, lefts, rights, lefts, rights, lefts, where n sub I are all going to be non-zero integers. N1 or Nk may be 0 if it begins or ends with a left turn. N sub I greater than 0 indicates forward turns, and N sub I less than 0 indicates reverse turns. Allowing for forward and reverse turns give rise to an extension of Calkin Wilf tree. I've seen this before. This is a particular fractal. In this case, it's generated by a four-way tree of fractions. Figure 12, Gobler. Every fraction, including 1 over 0, appears infinitely often in a four-way tree. In order for T infinity to be well defined, we select T infinity to be right, left, inverse to be the canonical Taffy pole for the Taffy number 1 over 0, noting that the diagram of right, left, inverse is indeed the 180-degree rotation of T0. When two generalized Taffy poles have the same Taffy number, how do their diagrams compare? So, for example, the generalized Taffy pole of T equals R2L1R inverse, shown in figure 11, has Taffy number -1/3, and the canonical Taffy pole for the Taffy number -1/3 is T star equals right inverse left inverse 2, whose diagram appears in the upper right corner of the double tree in figure 10. Remarkably, diagrams are identical. Cool. Let T be a Taffy pole. Diagram T left right inverse is the 180-degree rotation of diagram T right. Composition of turns left right inverse rotates the leftmost peg underneath both pegs to its right. Same motion of the pegs is achieved by a right turn followed by a 180-degree rotation. Hence, T left right inverse is also the 180-degree rotation of T right. Alright, so left gets us the left one to come up this way, and right inverse will bring this underneath right. Normally, a right turn will bring this over the top and fix the middle into the third slot going up. But instead, if it goes down, then it's just stretching all the way underneath. What if we add random orientation? Then the machine will break. Analogous statements hold by similar analysis. Right, left, inverse right, right, inverse, left are 180-degree rotations of the respective. Let T be a canonical Taffy pole, S be a single turn. The Taffy pole TS is equivalent to canonical Taffy pole with the same Taffy number as TS, whatever it might be. Proof given. Cool. Let T be generalized, then T is equivalent to the canonical Taffy pole with the same Taffy number. Proof here. Two generalized Taffy poles are equivalent if and only if they have the same Taffy number. Proof given. Getting tangled. The notion of a tangle in knot theory is used to describe the interactions between strands in the knot diagram. By wrapping a sphere around a portion of the knot, the interior space isolates a number of arcs with their ends on the surface of the sphere. Such a collection is called a tangle. So here we have yep. Conway introduced a family of two arc tangles called rational tangles to provide convenient notation for enumeration of knots and links. More recently, rational tangles have become valuable representation of molecular biology for studying DNA topology, protein folding, and all that good stuff, I'm sure. In this section, we consider rational tangles as combinatorial objects with connections to the Calkin wolf tree, because a rational tangle begins with a pair of horizontal arcs with their ends positioned on the four corners of a square. Ends may be twisted around each other in two ways: vertical twist and a horizontal twist. Yeah, so initially horizontal twist won't do anything. If we do a vertical twist, then they end up crossing each other. Right? If we do another vertical twist, then they end up interlinked, like that. And then if we do horizontal twists on top of that, we end up getting more tangled type looking stuff. Vertical and horizontal twist can be undone. We call these reverse motions a vertical untwist and horizontal untwist. Same stuff as always, right? In a tangle diagram, twists and untwists are distinguished by crossings that they form. Each twist, whether vertical or horizontal, forms a positive crossing. Each untwist forms a negative crossing. We define a rational tangle to be any finite sequence of vertical or horizontal twists or untwists. By now it should come as no surprise that the four types of twists can be associated with the directions of movement in the four-way tree in Figure 12. To each tangle, we assign a tangle number, Q of t, given by the fraction at the end of the path from the four-way tree. From the discussion above, the continued fraction whose coefficients are the numbers of consecutive steps. This is all the same stuff, and how Conway assigned rational numbers to rational tangles in his original presentation. So this is the same stuff that we were talking about with the one above. Conway's result is that the two tangles, any two rational tangles, have the same tangle number if and only if their diagrams are equivalent up to ambient isotopy. Diagrams of T1 and T2 are ambient isotopic if the arcs of T1 can be continuously deformed into those of T2 without moving the endpoints and without arcs passing through each other or leaving the square boundary formed by the endpoints. Draw the sword, cut the mess. Well, yeah, but then like way more of these knots end up becoming equivalent. Twists and turns, again. Taffy diagrams and rational tangle diagrams are structurally similar, and they both consist of points and arcs. Four features align at once, will align once the tangle diagrams are rotated 45 degrees clockwise. Comparing rotated initial rational tangle to the initial taffy pole, three endpoints in tangle are roughly arranged like the pegs of the taffy machine. So here, right, connection between the leftmost two, if we omit the one at the top in every case, right, then through a partial rotation, you're always going to end up with a similar, if not identical, diagram. Making twists and turns in tandem, we explore these visual similarities. After a vertical twist and right turn, corresponding features of tangle diagram resemble those of the taffy machine, albeit somewhat abstractly. After transformation, the second arc in the tangle diagram is positioned as one of physical pegs of the taffy machine, in sight easy to miss when only viewing cross-sections of the taffy machine. From this observation, it's revealed that the taffy machine is truly a tangle machine. The two arcs that get tangled together, and the taffy machine, and the third peg that is not attached to the taffy. How beautiful indeed. With apologies to Sir Walter Scott. Oh, what a tangled web we weave when first we studied taffy trees. Right out. Interesting overall paper there, so cool stuff. Oh. No, okay. That got me worried there. Euler's work on spherical geometry, an overview with comments. We're going to head out to ad break for 3 minutes. Get up and get V a snack or water or other drink or whatever it is that you need, and we shall return shortly. So get any requests in if you want to punish me with exercises. We'll see you in 3. Alrighty, we're back. Got really quiet. What is it? There you go. There we go. Back home. Massif. Don't know who that is. Anyway, just because I need to punish myself. These standard 20 push-ups, which is never going to go well. Admittedly, this is better than it has been, so just gonna get properly. Don't break it. Hang on. 17. Hate push-ups. It's one of the reasons I put it on there. Let's put this at the end here. Where'd it go? Oh no, what did I do? There we go. Okay, after an introduction concerning the general place that trigonometric formulae occupy in geometry, we start by the two memoirs of Euler. On spherical trigonometry, in which he establishes the trigonometric formulae using different methods, namely the calculus of variations in the first, and classical methods of solid geometry in the second. In another memoir, Euler gives several formulae for the area of a spherical triangle in terms of its side lengths. See spherical Heron formulae. He uses this in the computation of numerical values of solid angles of the 5 regular polyhedra, which is his stated goal in the memoir. Then review memoirs in which Euler systematically starts by establishing a theorem or construction in Euclidean geometry and proves the analog in spherical. We point out relations between Euler's memoirs on spherical geometry and works he did in astronomy, on the problem of drawing geographical maps, and in geomagnetism. We also review some other works of Euler involving spheres, including a memoir on a three-dimensional Apollonius problem, and others concerning algebraic curves on a sphere. Even though these works are not properly on spherical geometry, they show Euler's interests in various questions related to spheres, and we think that they are worth highlighting in such an overview. Beyond spherical geometry, the reader is invited to discover in this article an important facet of the work of the great Leonard Euler. Article will appear as a chapter in the book Spherical Geometry in the 18th Century 1. Euler, Lagrange, and Lambert. Spring 2026. Tonight's just a little bit of iced tonic water. No gin on this trip, so. Introduction. Review Euler's memoirs in spherical geometry, together with works that include work on spherical geometry in a broad perspective. Plan is the following. Blah, blah, blah. We did a lot of this already. Euler's memoirs on this subject, namely Principe de la trigonométrie sphérique tiré de la méthode des plus grands et plus petits. Principles of Spherical Trigonometry deduced from the method of maxima and minima. Published in 1755, Trigonometria Spherica Universa Exprimis Principis Breviter et Delucide Derivata. General spherical geometry deduced from fundamental principles in a brief and clear manner. Didn't study Latin. Published in 1782. In each of these two memoirs, Euler establishes a set of formulae of spherical geometry. In the first, he uses the proofs of these formulae, methods of differential geometry, and calculus variations, whereas the second he relies on more classical proofs that are based on the geometry of the 3D Euclidean space, cutting planes and solid angles defined by a spherical triangle, and applying to the resulting Euclidean triangles the formulae of plane trigonometry. Hui. Section 4, talk about de mensura angulorum solidorum, on measure of solid angles, in which he gives geometrical proof of Girard's formula for the area of spherical triangles, which is intrinsic to the sphere. Proof begins with a remark on the areas of lunes on the sphere. Goes back to Bonaventura Cavalieri. Same memoir, Euler obtains several formulae for the area of spherical triangle as a function of its side lengths, using analytical tools. Alright. In the Euclidean case, the locus of... proves a result in spherical geometry, which is the analog of well-known result in Euclidean geometry, namely a description of the locus of the vertices of triangles having a fixed base and fixed area. In the Euclidean case, this locus is a straight line, and the result is contained in Euclid's elements. In the spherical case, the locus is not a geodesic, and the result is more complicated to prove. Euler attributes the problem and the result to his young collaborator Anders Johann Lexell, who wrote a memoir on the subject. Cool. More after that. Okay. The expression spherical trigonometry refers to a set of formulae that make relations between the side lengths and angles of a spherical triangle. Such formulae constitute a non-negligible part of Euler's mathematical heritage. In fact, even before writing his memoirs on the topic, Euler used extensively spherical trigonometry in his works on geography, astronomy, and geomagnetism. But in our opinion, the importance of spherical geometry goes beyond these applications, as we shall explain later in this chapter, after including the question in a broader context. First of all, let us state a general fact, namely that the set of trigonometric formulae relative to a given geometry is an important aspect of that geometry. perhaps the most important. Indeed, geometers know that the basic features of geometry are contained in the properties of its triangles. The properties of the small and infinitesimal triangles tell us about local property of geometry, and the properties of large triangles tell us about the large-scale properties. John Napier, in number 67 in 1614, highlighted the importance of the trigonometric formulae. The following quote by Napier is borrowed from Annette Acampo's chapter in the present volume. Since geometry is the act of measuring, the art of measuring proposed quantities with complete accuracy, and as a figure can be decomposed into the sides of triangles, or by further triangulation into smaller triangles, then a figure is composed of triangles with some of its angles and sides measured, and all the other triangular parts are to be found, and from which the extent of the figure can be found. Therefore, it is clear that the arithmetical solution of any geometrical question depends on the principles by which the triangles are solved. It is interesting to remember in this respect the great Lobachevsky, when he started establishing the basis of geometry that carries now his name, was very careful in establishing a complete set of trigonometric formulae. Less well known is that Lobachevsky was very much concerned about the question of non-contradiction of geometry, argued that if there were a contradiction in his geometry, then it would be a contradiction stemming from the associated trigonometric formulae, for the reason we have just explained. Lobachevsky and Bolyai both were better known for their hyperbolic space geometry. He had proved his hyperbolic trigonometric formula using solely the geometry of Euclidean plane and the sphere. Most spherical geometry was done, 1,000 years ago, basically. And then Euler was able to expand upon it and get most of the, again, trigonometry and calculus done on spherical geometry. And then hyperbolic geometry was a product of the 1800s. Lobachevsky, without having a Euclidean model of hyperbolic geometry, reduced the non-contradiction problem of his geometry to that of Euclidean geometry. The fact is little known. Let us quote the remarks that he made on this question at the ends of Elements of Geometry, translation from page 7, reference 75, page 223. After we have found the equations, which represent the dependence of the angles and sides of a triangle, and we finally have given the general expressions for the elements of lines, areas, volumes of solids, all else in geometry is a matter of analytics, where calculations must necessarily agree with each other. We cannot discover anything new that is not included in these first equations, from which must be taken all relations of geometric magnitudes one to another. Thus, if one now needs to assume that some contradiction will force us to subsequently refute the principles that we have accepted in this geometry, then such contradiction can only hide in the very equations 17. We note, however, that these equations become equation 16 of spherical geometry as soon as, instead of the sides ABC, we put a root 1, a root negative 1, b root negative 1, c root negative 1. But in ordinary geometry and in spherical trigonometry, there enter everywhere only ratios of lines. Therefore, ordinary geometry, trigonometry, and the new geometry will always agree amongst themselves. It is also good to note that the trigonometric formulae, spherical and hyperbolic, are already contained in Lobachevsky's first memoir, The Elements of Geometry, and in his later works such as Geometrische Untersuchungen, 65, cool. Talking about the importance of the geometry of triangles, let us also recall that a large portion of the geometrical part of Euclid's Elements, and Menelaus Spherics is the study of Euclidean, respectively spherical triangles, even if none of these treatises contains trigonometric formulae. Let's also recall that Herbert Boozman and A.D. Alexandrov and M. Gromov developed geometric theories that are based on a property of triangles, see 10, 3, and 52. Finally, let us recall that W. Thurston in Geometry and Topology of Three Manifolds, A1, which arguably was the most influential 20th century work on geometry and topology, starts by establishing a set of trigonometric formulae for spherical and hyperbolic geometry. On Euler's work on spherical geometry. Okay, regarding the above memoirs, we start by quoting Rosenfeld from his History of Non-Euclidean Geometry. The modern form of spherical geometry, as well as all trigonometry, is due to Leonhard Euler, native of Basel, who worked in Petersburg and Berlin. Whereas trigonometry before Euler was concerned with trigonometric lines, Euler's trigonometry dealt with trigonometric functions, which he linked to exponential function by means of sinus totus, the complete sine, that is, the radius of the circle, replaced it with unity. In ancient sine tables, sinus totus appeared as the radius of the circle that was used to construct this table. It corresponds there to the value of sine of 90 degrees. To describe in some detail Euler's two memoirs, let us first recall that a spherical triangle is a figure on a sphere consisting of 3 points, vertices, together with the shortest possible segments, the sides, joining them pairwise. Thus, a spherical triangle gives rise to 6 quantities: the 3 angles at the vertices and the 3 side lengths. That's not really surprising, same on the plane. However, by the usual criteria of equality of spherical triangles, the knowledge of any 3 of these 6 quantities determines the triangle. Trigonometric formula is typically a relation between 4 or more of these quantities. In each of his two memoirs, Euler derives a set of trigonometric formulae that can be useful in various situations involving a wealth of variables like sums or differences of pairs of sides or of angles, etc. First, consider Euler's memoir, Minima and Maxima. Right. In the introduction, Euler addresses the question of why one should use the methods of minima and maxima, that is, the calculus of variations, to establish trigonometric formulae, while simpler methods exist. First answer is 3 points. 1, it's just cooler. First, the methods of minima and maxima, he says, acquire a new domain of application in the field of spherical geometry. Indeed, it seems that this is the first time that trigonometric formulae are established using this method. It should be recalled that methods of calculus of variations since their introduction by Euler and then Lagrange have been especially useful in the solution of problems of physics, even if these methods were formulated as a part of mathematical analysis. Euler's memoir, Latin, method for finding curved lines enjoying properties of maximum and minimum, or solution of isoperimetric problems in the broadest accepted sense, in which he gives a general presentation of the problems that are dealt with, using the calculus of variations as well as an exposition of the general methods for solving them, contains, by way of illustration, a list of 100 special cases to which the general methods apply. These problems include a solution to the brachistochrone problem, awesome, others related to the principle of least action, others in geometric optics, and many more, all originating in physics. Talking about the calculus variations, Euler writes in his memoir, since we have shown that most of the mechanical and physical problems can be resolved very promptly with the aid of such a method, it cannot be but very pleasant to see that the same method brings such a great help for the resolution of problems of pure geometry. Okay. Cool. 2. Euler declares that it's always useful to have different proofs of the same result, that this will help for better understanding of the result. I completely agree. I have done numerous proofs of various things that I'm trying to show my classes, and invariably there's always somebody who doesn't quite get it one way but gets it a completely different way. And 3, Euler states that the methods of maxima and minima, unlike the previously known methods for deriving trigonometric formulae, are very general and can be applied to arbitrary surfaces. So, yes, right, if we can apply this to any surface that has a like the same curvature as a sphere, so that is considered positive curvature. Right? If we can apply it to any curve that has positive curvature, that's pretty awesome. Considering the third point, one may recall that in the memoir Éléments de la trigonométrie sphéroïdique tirée de la méthode de la plus grand et des plus petits, is published in the same year as the other one with the methods of maxima and minima. Euler studies triangles on a spheroid, and that he even starts there by considering triangles on an arbitrary surface. Let us quote from that memoir: having established the elements of spherical trigonometry on the principle of maxima and minima, my main goal was to fix such a general principle from which one could extract the resolution of triangles formed not only on a spherical surface, but in general on an arbitrary surface, since the sides of a spherical triangle are arcs of great circles, which, being the shortest paths that one can draw on a surface of a sphere from one point to another, it is on equal footing that I consider the sides of a triangle described on any arbitrary surface in such a way that they become the shortest paths that lead from an angle to another on this surface. And let us return to 25. Euler starts by recalling the definition of a spherical triangle. The idea that using calculus variations in this setting is based on the fact that an edge of such a triangle is a geodesic on the sphere that is the shortest path between endpoints. Finding the length of the side of a spherical triangle becomes a variational problem. The first result is Euler's paper on the solution of this problem, where in the case where the side whose length is sought is opposite the right angle. Right, so the hypotenuse, what we would generally consider on the plane. More precisely, it gives a solution to the following problem. Given an arc AP on the equator and arc PM on a meridian, find on the spherical surface the shortest line AM that can be drawn from point A to point M. The use of geographical terminology in this statement is not unexpected, since Euler had in mind the example of the Earth, generally identified with a sphere in the problems of drawing geographical maps, in which he had been heavily involved. As in several other memoirs, main results are presented in the form of problems and corollaries. Euler starts by establishing a list of 30 formulae involving only 3 variables, valid for the case of a right triangle. Given any 2 quantities, sides or angles, he gives 3 formulae giving the values of the remaining ones. Using this, he obtains a large collection of trigonometric formulae for general, if not necessarily right, triangles involving sides, angles, and various combinations of them. Among them are formulae for the value of a side of a spherical triangle in terms of the three angles. Obviously, such formulae cannot exist in Euclidean geometry, where the angles do not determine the sides. The memoir concludes with a proof using differential and integral calculus on the formula attributed to Albert Girard, which gives the area of a spherical triangle in terms of its angle excess. Beyond the obtention of trigonometric formulae, Euler developed in the memoir, using the calculus of variations, a variation of the intrinsic differential geometry of surfaces embedded in 3-space, theory that Gauss and after him Riemann continued to develop in the century that followed. It's also mentioned in respect, Memoir de Lineana Bravimicia, in superficie quacunque duo quaelibet puncta ungente, on the shortest line joining 2 points on a surface. Published in 1729, Euler, who was 22 at the time, established the equation of a geodesic on an arbitrary surface. Good job. At 22, I had barely passed my bachelor's. In the memoir, General Spherical Trigonometry Deduced from Fundamental Principles in a Brief and Clear Manner, published in 1782, Euler recovers the trigonometric formulae in a more classical manner by methods of the ambient three-dimensional space with no differential or integral calculus. Starts by establishing the three basic formulae: sine c over sine little c equals sine big A over sine little a, cosine big A sine little c equals cosine little a sine little b minus sine little a cosine little b cosine big C, and cosine little c is equal to cosine little a cosine little b plus sine little a sine little b cosine big C, from which he derives the rest of the trigonometric formulae by performing algebraic transformations. Right at the beginning of the memoir, Euler notes that the choice of notation capital ABC and lowercase abc for the angles and the sides opposite to them leads to the set of symmetric formulae. He highlights a rule for obtaining new formulae out of known ones. This rule turns out to be a form of duality theory in spherical geometry, or the theory of the polar triangle. This discovery was attributed by Michel Chasles, the famous mathematician and historian of mathematics, to François Viète, but it is now known that this discovery was already known to Arab mathematicians in the 10th century. See historical exposition in chapter 10. Several authors after Euler worked out, like him, a complete system of trigonometric formulae based on very few starting formulae, mentioned in particular Lagrange in Mémoire solution de quelques problèmes relatifs au triangle sphérique avec une analyse complète de ces triangles. Solution of some problems relative to spherical triangles with a complete analysis of these triangles. Published in 1799, translated into the present volume. And de Gouin, whose work on the subject came shortly after that of Euler and before that of Lagrange, and end the section by quoting Delambre from Rapport historique sur les progrès des sciences mathématiques depuis 1789. Historical report on the progress of mathematical sciences since 1789, who includes Euler's work in the broader context. Euler, in a memoir printed in 1779, had reduced spherical trigonometry to a fully analytical form. Since everything is determined in a triangle, of which we know, for example, two sides and the included angle, it follows that the whole of trigonometry is contained in the equation which serves to solve this particular case. To extract it is purely an analytical problem. However, it does require some skill. It is not even useful to know in advance what one is looking for. The problem, moreover, was only a game for Euler. Monsieur Lagrange, in treating the same subject in the sixth cahier of the Journal de l'École Polytechnique, added some curious propositions concerning the area of the spherical triangle and the pyramid for which this surface serves as a base. It should be noted, however, that this new way of considering trigonometry added almost nothing to the formulae we had in our possession. We should not be surprised the astronomers who made continual use of these methods had turned them upside down in every way. They had even arrived at solutions which are astonishing in their symmetry and elegance when we consider the elementary means by which they had reached there. The research of Euler and Lagrange made the analytical method as elementary as the old one, and since that time several geometers, Monsieur Bertrand Lacroix Puisson and several others, have varied this development, which in fact can be explained in several ways, starting with whichever of the particular formulae one wishes. Given only one, the rest will follow. To end this section, let us note that Euler, Lagrange, and Lambert, in their memoirs on spherical trigonometry that are published in the present volume, all worked out sets of formulae that are suitable for computations with logarithms, that is, involving multiplications rather than additions. This was important for computations and for establishment of tables that were used in astronomy and geography. Rock. On the measure of solid angles. Right, we're here. 1, 2, 3, 4. Cool. Spherical area is the central theme of Euler's memoir, De Mensura Angulorum Solidorum, the measure of solid angles. In this memoir, Euler's goal is to compute numerical values of solid angles of the 5 regular polyhedra. But the measure of a solid angle in this area of the region of the sphere of radius 1, centered at the vertex of this solid angle. This is the three-dimensional analog of the fact that the measure of an angle in the plane, whose vertex is the center of a circle of radius 1, is the length of the arc of circle subtended by this angle. Thus, the computation of solid angles becomes a question of computation of area in spherical geometry. The simplest case is that of the solid angle formed by joining pairwise along their edges 3 Euclidean angles. In this case, the value of the solid angle is equal to the area of the spherical triangle. Euler recalls in the memoir considered that, according to Girard's formula, the area of the spherical triangle is equal to its angle excess with respect to right angles. He starts by giving a very simple proof of Girard's formula based on the computation of areas of lunes. A similar proof was given by John Wallis, 1616 to 1703. Lune in spherical geometry is a region on the sphere bounded by 2 half great circles. That is, a lune is bounded by 2 geodesic segments joining a pair of antipodal points, figures 1 and 2. ACBDA is a lune. In the middle figure, we have 3 lunes, right? So 1, 2, 3. Alright, similar proof was already given by John Wallace, who attributes it to Bonaventura Cavalieri, figures 1 and 2 above, extracted respectively from Wallace's and Euler's memoirs. The drawings summarize the main ideas of the proofs, and their similarity is an indication of the fact that the two proofs are the same. The excerpt from Wallace's proof up here, reproduced in figure 1, mentions the names of Girard and Cavalieri. Alberto Girardo, Cavaliero, Cavalieros, regarding these so-called Girard formula, let us note additionally that Lagrange, in his memoir Solution de quelques problèmes, etc., which is translated into the present volume, writes the following: we should rather attribute this theorem to Cavalieri, who gave it to the Directorium Generale Uranometricum, printed in Bologna in 1632, with beautiful proof reported on by Wallace and inserted since then in most of the trigonometries. After the proof he gives in 33, so-called Girard formula, Euler establishes several formulae for the area of spherical triangle in terms of its side lengths. This is the same as when I call it the so-called Pascal triangle. More likely, I usually call it the Euler triangle, but you have to be able to understand it. So. Euler establishes several formulae for the area of a spherical triangle in terms of its side lengths. This is a spherical analog of the Euclidean Heron formula. This allows Euler to give numerical values for the solid angles of all 5 regular polyhedra after he solves the following problem. Given a solid angle consisting of n planar angles which are equal to a certain quantity A and which are equally inclined amongst themselves, to find the measure of a solid angle. It is conceivable that this is the first time in history where numerical values of the solid angles of the 5 regular polyhedra are computed. Incidentally, after Euler gives the spherical Heron formula, he shows that it reduces to the usual Euclidean Heron formula when the 3 sides of the spherical triangle become infinitely small. Locus of spherical triangles within a given area. In the memoir Variae Speculationes Super Area Triangulorum Sphericum, various speculations in the area of spherical triangles, published in 1797, Euler starts by giving several formulae for the area of spherical triangles as a function of its side lengths. He then considers the problem of finding the locus of the vertices of a spherical triangle with given base and fixed area. The analogous problem in Euclidean case is the subject of propositions 39 and 37 in Book 1 of Euclid's Elements. In this case, the desired locus is a straight line. At the same time, Euclid proves that any triangle in this family of triangles can be cut into pieces that can be joined together to form a square having the same area as the initial triangle. 37, 39 in Book 1, you say? Triangles which are on the same base line and in the same parallels are equal to one another. So, okay. So this is if you were to draw a base of a triangle and then draw multiple triangles from here to a parallel line up here, anywhere, right? Draw that triangle, draw that triangle, draw that triangle, draw that triangle. As long as you haven't moved your base points, you haven't moved your parallel line up above, then those areas must be the same. And 39, equal triangles which are on the same base and on the same side are also in the same parallels. ABC and DBC, same base. On the same side. Let's on the same side of it. Okay, so they both have points above their shared base. Oh, equal triangles, which are on the same base and on the same side, must then have the same parallel. That makes sense. Okay. It's an equal triangle, so it's like the identical triangle. We would call it congruent these days, I'm pretty sure. Anyway. So here they'd be talking about using oh, that's fun. Because no two no two lines on a sphere are going to ever be parallel, right? They represent two great circles, so they're always going to create a lune between them. It's not possible for it to be parallel, but this does have an analogous problem. So they have a given base, meaning that they have the same great circle upon which we draw 2 points, and that is the shared base of those two triangles. And then they connect to a separate great circle, and they have equal areas. So what relationship do they have? Euclid proves any triangle in this family of triangles can be cut into pieces that can be joined together to form a square having the same area as the initial triangle. Elements does not actually contain definition of area, but only the notion of two figures having the same area. The fact that two figures can be cut into pieces and can be glued back together to form the same figure says that the two initial figures must have the same area. Unlike the Euclidean case in spherical geometry, the sought locus is not a straight line, i.e. a great circle, but rather a small circle. That is, a locus of points equidistant from a great circle. Nice. Furthermore, contrary to what one might think, by analogy with the Euclidean case, the great circle in question is not one containing the base of the triangle. Interesting. Occasion for these reflections was given to him by the theorem made known by his young collaborator Anders Johann Lexell. Lexell wrote a memoir on the subject titled Solutio Problematis Geometrici ex Doctrina Sphericorum. Solution of a geometric problem in spherical geometry. This memoir is analyzed and commented on in the sequel of the present volume. Sorlin and Jagon, 1825 article, give a solution that is now called Lexell's problem, without quoting Euler, but quoting Lexell and Legendre. Lebesgue published a paper titled Démonstration du théorème de Lexell, proof of Lexell's theorem, in which he gives a proof of the theorem that is, in fact, Euler's proof. Whoops. At the end of that paper, the editor of the journal adds a comment saying that Eugène Catalan, in his Éléments de géométrie, Book 7, Problem 7, gives a proof of Lexell's theorem. Catalan does not mention Euler. The only original contribution of Lebesgue in this paper consists of 2 remarks that he makes after the proof. First one says that there is an analogous result for surfaces of revolution which emit an equator. The second remark says that by taking the stereographic projection of the figure on the sphere, we get a family of curved triangles in the Euclidean plane that have a given base whose angle sum is constant and whose vertices are on the same circle. Other memoirs from Euclidean to spherical geometry. We've already noted that so-called Lexell problem, which Euler studies in spherical geometry, is the spherical version of the result contained in Euclid's Elements concerning the locus of vertices with triangles having the same base and fixed area. We also said that the memoir on measure of solid angles, Euler gives a spherical analog of the Euclidean Heron formula for the area of triangle in terms of its side lengths. There are 2 other memoirs by Euler translated in present volume, in which Euler obtains results in spherical geometry that are analogs of results in Euclidean geometry. We shall now discuss them. In the memoir Problematis Cuiusdam Papi Alexandrini Constructio, Construction Relative to a Problem of Pappus of Alexandria, published in 1783, Euler solves in the Euclidean and then spherical settings a problem inspired by a construction of Pappus from the collection. Pappus of Alexandria was a prominent mathematician who lived around the end of the 3rd century and was the first half of the 4th century. His major work and substantial part of which has survived, called The Collection, Synagogue, which contains mathematical results, some of which are difficult to prove, covering much of geometry. His name is attached to a theorem concerning the alignment of 3 points, which is therefore not the one Euler is talking about, which is at the foundations of projective geometry. Pappus also introduced the notion of anharmonic ratio. Collection contains a host of theorems with detailed proofs, sometimes several proofs, some of which are difficult, which are not due to him, but which would have come down to us without him. Some are taken from works by Euclid, Archimedes, Heron, Apollonius, and others which are completely lost. Collection contains results in Euclidean geometry, spherical geometry, analytic geometry, astronomy, mechanics, as well as problems of the type that would today be called recreational mathematics. Nice. Jean-Étienne Montucla, in this thing, writes that Pappus gives in his mathematical collection marks of an uncommon intelligence in geometry, and in several places one finds traces of genius. Among the mathematicians who have immersed themselves in the study of Pappus, at least René Descartes, Thomas Simpson, and Michel Charles should be mentioned. The latter published a work which he called Les Trois Livres du Poéisme d'Euclide, rétabli pour la première fois d'après la notice et les lemmes de Pappus, et conformément au sentiment de R. Simpson sur la forme des énoncés et de ses propositions. 3 books of Euclid's Porisms recovered for the first time, according to the notice and lemmas of Pappus, and in accordance with the feeling of R. Simpson on the form of statements in these propositions. My goodness. Work is entirely drawn from Pappus's collection, which is both a great source of inspiration for mathematics and an invaluable document on the history of mathematics. Introduction to Book 7 of that work contains a significant amount of unique information on ancient mathematicians and their results. Nice. Okay, spherical setting, problem inspired by the construction of Papas from the collection. Proposition 117, Book 7. Problem is to construct a triangle which is inscribed inside a given circle whose 3 sides are contained in 3 lines that are required to pass through 3 given points. The construction is non-trivial. Papas gives this construction in the Euclidean setting and only in the special case where the 3 given points are collinear. Problem has attracted the attention of several prominent mathematicians in the same volume of Acta in which Euler's memoir was published. Yet another solution of the same problem in the spherical setting as well was given by Nicolas Fuss, another young collaborator of Euler, in a memoir titled Solutio Problematis Geometrici Papi Alexandrini. An elementary solution by Lagrange of the same problem, based on trigonometric formulae, appeared in the memoir Solution algébrique d'un problème de géométrie, whose English translation is contained in Chapter 17. Michel Schall, in his Aperçu historique sur l'origine et le développement des méthodes en géométrie, has a note on the history of this so-called Papas problem. According to this account, Euler's proof may be traced back to the theorem attributed to Scottish mathematician Matthew Stewart concerning 4 points taken arbitrarily on a straight line. We also learned the same source in 1782, the Swiss mathematician Gabriel Kramer. I wonder, is that the same guy as Kramer's rule for matrices? Named after Gabriel Kramer, who published the rule on an arbitrary number of unknowns in 1750, although Colin Maclaurin also published some special cases of the rule in 1748 and possibly knew of it as early as 1729. So yes, same guy. Gabriel Kramer proposed this problem in general Euclidean setting of non-collinear points to Johann Castillo, and the latter published his solution in 1776, Nouveau Mémoire de l'Académie Royale des Sciences et Belles-Lettres de Berlin. It's interesting to note that both Kramer and Castillon were correspondents of Euler, first one between 1743 and 1751, and second from 1745 to 1765. Correspondence published in 45. Schall also noticed that Annibale Giordano, a 16-year-old Napolitan, and Gianfrancesco Malfatti solved a more general problem in which a triangle is replaced by a polygon with an arbitrary number of sides passing through an equal number of points. Their works are published in Volume 4 of the Memorie della Società Italiana delle Scienze dei 40, in the Berlin Memoirs of 1796 with mathematician Simon Liouville. Published a modified algebraic solution to the same problem. Lazare Carnot, in his Géométrie de position, gave a modified form of Lagrange's solution and applied it to the case of an arbitrary polygon, a case already considered by Giordano and Malfatti. Schall also mentions solutions to generalizations of Papas's problem by Charles-Julien Brianchon, in the case where conic section replaces the circle, and where the 3 points are aligned by Joseph Diaz Gergon. in the general case considered by Brianchon, and allowing a solution with only straight edge, no compass, and by Jean-Victor Poncelet, who in Traité des propriétés projectives considers an extension to the case of the polygon in an arbitrary number of sides where the circle is replaced by an arbitrary conic. Detailed mathematical commentary on Euler's result presented by this memoir, various approaches and generalizations by other mathematicians are provided by Guillaume Thierry in Chapter 4 of the present volume. Hey, now we have some actual formulas. Just slightly more than halfway through. Oi. Alright, so there appear to be a lot of products of ratios, which end up getting us interesting ideas here. Hyperbolic tangent. Euclidean case, Euler derives several different proofs of the theorem and its converse. In the Euclidean plane, given three segments, AO little a, BO little b, CO little c, meeting at a common point O, and satisfying the above equation, AO over O little a times BO over O little b times CO over O little c is equal to the same products. Oh no, the same sums plus 2. We can construct a triangle ABC, big ABC, such that the points little ABC are on the sides, BC, AC, AB, respectively. Jeez. And then the new condition involves tangents. This is bonkers. Okay. Yeah. Maybe we'll discuss more next time, but for right now, I think we're running short on brain power. So let's try and find, is Dr. Gold on? I do not see him right now. So let's go check out. He might be up in 3 minutes. If that's the case, I will be very sad. Come on. No, tomorrow. Okay. Okay. So I won't be sad. Let's go see Casey Snow Art, who is currently working on Community Art Showcase. Working on the Vaquita sticker sheet. We'll go see some of our other friends who are here from Science streams, and a few other people who I recognize from other community areas. I hope to see you all tomorrow. We'll be doing 9 Souls. We'll try to beat Igong again. We'll see how this goes. We're very slowly but surely advancing just a little bit every single time we do this. So we may have to play again on Thursday and or Friday to try and beat Igong. We are also working at completing some stuff for Elite Dangerous to prepare for our new big trip that we're doing. We are working on getting our ships ready to go on Distant Worlds 3, which is the extremely distant exploration mission, which is going to like a section of the galaxy that nobody has gone to yet. So, should be interesting. Hope to see you all then, and if you're here for just mathy stuff, I'll see you on Wednesday. We'll do some calculations. We'll start with problems out of cracking the GRE, and if anybody has any questions, we'll take them. So, hope to see you all then. Good luck, everybody. Have fun, stay safe, all that good stuff. And my name's Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.